Hello everyone and welcome to today's WhatsApp webinar. Today we are going to look at dental rotary instruments, the different types, materials, designs, as well as a few guidelines on how one can select the best dental rotary instrument. To start off, let's first understand what rotary cutting instruments are. Rotary cutting instruments are a group of instruments that turn on an axis to perform cutting, abrading, burnishing, finishing, or polishing of a tooth structure or restoration. The devices used for cutting are handpieces, which are power devices, and burrs or abrasives, which are cutting tools. Handpieces are devices that hold and transmit power to the rotating instrument and help to position and control the rotating instrument intraorally. On the other hand, dental burrs or abrasives are rotary instruments used to cut or grind hard tissues such as enamel or bone. These are available in a range of shapes, sizes, and grids with sharp-edged blades and cutting edges. There are two main types of handpieces: straight handpieces and contra-angled handpieces. In straight handpieces, the long axis of the burr is the same as the long axis of the handpiece. These types of handpieces are used more commonly for laboratory work, and occasionally they are useful clinically as well for chair-side adjustments. Contra-angled handpieces are those in which the head of the handpiece is first angled away from and then back toward the long axis of the handle. This design brings the head of the burr close to the long axis of the handle of the handpiece. Due to this, there is a balance which helps to stabilize the handpiece and improve access and visibility. Contra-angled handpieces are primarily used intraorally. Contra-angled handpieces are further divided into two types: micromotor handpieces and air rotor handpieces. Micromotor handpieces are attached to an electric micromotor or an air motor, while air rotor handpieces are attached to the air-water line of the dental unit and are activated by compressed air supplied by a compressor. Micromotor handpieces operate in the speed range of 500 to 50,000 rpm, while air rotor handpieces operate above 2 lakh rpm. Micromotor handpieces have less speed and higher torque, while air rotor handpieces have lower torque. Micromotor handpieces contain a water spray to operate at the highest speed range, while air rotor handpieces contain flow-through system to direct air-water spray at the cutting edge of the burr, which dissipates the heat generated during the cutting action. Rotary instruments operate in three main speed ranges: low speed below 12,000 rpm, medium speed between 12,000 and 2 lakh rpm, and high speed above 2 lakh rpm. Low speed rotary instruments are used for caries excavation, refining cavity preparations, and finishing and polishing restorations. They provide the operator with a good tactile sense, but are often inefficient, time-consuming, and need heavy pressure, causing production of heat and vibrations during cutting. This causes a reduction in their longevity and increased patient discomfort and operator fatigue. Medium-speed rotary instruments are used for cavity preparation, preparation of retention grooves and bevels, and preparation in areas of limited visibility. They provide a positive tactile sense and a controlled cutting of tooth structure. However, they result in a slower cavity preparation, leading to increased operator fatigue and patient discomfort, as well as increased heat production. High-speed rotary instruments are used for the removal of old restorations, completion of cavity preparation, and tooth reduction for crown preparations. Their advantages are that they are able to prepare the tooth structure faster with less pressure, less heat, and less vibrations. They require fewer instruments to do the same amount of preparation, which improves burr longevity and provides ease of use for the operator with less patient discomfort. They also make quadrant dentistry possible. On the other hand, they provide less tactile sense, so it is more easy for the operator to overcut the tooth structure. Also, they result in increased chances for iatral errors, and the air-water spray can impair visibility. Now let us look at the parts of a dental burr. A dental burr has a head, a neck, and a shank. The head has cutting grooves, flutes, or blades positioned at different angles that produce cutting action by rotatory motion. The head is also available in a variety of different shapes and types used for different purposes. The neck attaches the shank to the head of the dental burr, connects the shank to the head, and transmits the rotational and translational forces to the head. The neck also has a color-coded band that is unique for every burr, indicating the different diamond grid sizes according to ISO classification. The shank fits into the handpiece, accepts its rotatory motion, and provides a bearing surface to control the alignment and concentricity of the instrument. It is available in different lengths and ends to enable attachment to specific types of handpieces. It is available in either stainless steel or plastic for multi-use or single-use respectively. Let's go deeper into the ISO classification of dental burrs. Each burr is coded with a unique 15-digit number according to 6 different characteristics. Each of these characteristics uses a 3-digit code to describe the burr. All manufacturers use this system of coding, making it easier for us to identify the exact burr that we need. The first parameter is the material of the head. This can be made of diamond, tungsten carbide, or steel. The next parameter is the shank type and the total length of the burr. This can be a handpiece shank, a right angle shank, or a friction grip shank. The next parameter is the shape of the head, which can be in a variety of different shapes, such as ball, inverted cone, pear, straight, taper fissure, etc. The fourth parameter is the size of the grid, which can be determined using 6 different colored bands on the neck of the burr. And the last parameter is the maximum diameter of the head, which is a 3-digit number that can be used to uniquely identify this number. There are 3 types of dental burr shanks. The HP or handpiece type of shank, which is a larger, longer shank used in slow-speed handpieces, having a diameter of 2.35 mm, used in both clinical and laboratory settings, and is defined by the ISO number starting with 1XX. The next type of dental burr shank is a friction grip shank, which is used in high-speed handpieces, has a diameter of 1.6 mm, its length is defined by ISO number starting with 3XX, and it can be used in RA handpieces after application of the FG to RA adapter. Lastly, we have the right-angled dental burr shank, which is used in low-speed contra-angled handpiece, has a diameter of 2.35 mm, and its length is defined by ISO codes starting with 2XX. Now, FG burrs can also be used in RA handpieces if they are used in conjunction with the FG to RA burr adapter. Dental burr heads are available in a variety of different shapes, but few of the most common ones are what we will look at now. First, we have the round burr, which is used to make the initial punch cut. It is also used in caries removal and preparation of retentive features. Next, we have the inverted cone burr, which is used to provide undercuts for amalgam cavity preparation. Then we have the pear-shaped burr, which is used to prepare undercuts with rounded internal angles for amalgam cavity preparations, and in Class 1 gold foil tooth preparation. Next is the straight burr, which is used for preparation of walls for amalgam cavity preparation. And lastly, the taper fissured burr for preparation of indirect restorations such as inlays and crowns. Now let's look at the types of dental burr grids. Dental burrs are available in a variety of grid sizes depending on their intended use. Coarse and very coarse grids are used for tooth reduction, while fine, extra fine, and ultra fine are used in polishing and finishing. For burrs that have larger particles, the area between the particles are reduced and they are closely placed. And during cutting, only a few particles come in contact with the tooth surface, which increases the pressure on each particle, resulting in a rough surface. Dental burr grits range from ultra-fine, extra-fine and fine to medium, coarse and very coarse, and can be identified by the corresponding color band that is present on the neck of the burr. Now we will look at the types of dental burr materials. The first is diamond burrs. These consist of a diamond powder which is bonded to a stainless steel frame. This diamond grit grinds away at the material, leaving a rough tooth surface which requires further polishing at the end. Diamond burrs are available in a variety of grit sizes, ranging from coarse and super coarse grits used for tooth reduction to fine and superfine grits used for trimming, polishing and finishing. Diamond burrs are used for reduction in tooth structure for preparation of direct and indirect restoration. They are also used for precision cutting, grinding, shaping, smoothing and polishing of composites, porcelains and zirconia. Diamond burrs are fast, smooth and high precision cutting tools and also are highly durable. But they have a shorter lifespan compared to carbide burrs, leading to a decrease in cutting effectiveness. The next most common type of dental burr material are burrs made out of tungsten carbide. These burrs have 8 to 40 fluted blades and can be straight or twisted. They slice or chip away at the tooth material, leaving the surface more aesthetically pleasing as compared to diamond burrs. They are used in cavity preparation, cutting of bone such as during disimpaction or bone contouring, removal of restorations and crowns, as well as in dental laboratories. Their advantages are that they are 3 times stiffer than steel, which makes them resistant to wear and tear and makes it so that they can maintain a sharper cutting edge and be used many times without becoming dull. They can withstand high temperatures and they don't grind the enamel, leaving a smoother surface than diamond burrs. They also have less vibration and chatter on handpieces. On the other hand, tungsten carbide burrs are brittle and have a tendency to fracture under pressure. Thus, they are best operated at high speeds with light pressure. Now, what are the main differences between diamond and carbide burrs and how can one select the best burr for one's needs? So, diamond burrs cause reduction of the tooth or of the material by grinding, whereas carbide burrs have the same action through slicing or chipping. Thus, diamond burrs may leave the surface that they are grinding with a rougher finish, while carbide burrs result in a smoother finish compared to diamond burrs. Therefore, it is more preferable to use a finer grit for diamond burrs or use a dental polisher after using a diamond burr, while carbide burrs can be effectively used for finishing. Diamond burrs are also best suited to perform precise work and are the preferred choice for porcelain, ceramic and metal restorations. Carbide burrs, on the other hand, do not create any discoloration of the surface that they are working on and thus are the preferred choice for acrylic, porcelain and gold restorations. Next, we move on to a few lesser common dental burr materials. Firstly, we have stainless steel burrs. They are used for removing dentine and for cavity preparation. They are also effective in cutting rough objects, such as in the case of removal of old restorations. They have the best cutting surface, a hard texture which makes them resist abrasion, good edge retention when combined with wear-resistant carbides. They also resist breakage and thus have lower maintenance, are more economical and have a longer working life. And they are also very flexible. But in the case of disadvantages, they chip and dull more easily than other dental burrs. Finally, we have ceramic burrs, which are used in the modification of acrylic parts used in dental operations and for the adjustment of thermoplastic materials. Their advantages are that since they do not conduct heat, they do not heat up like other dental burrs, and they also result in a lesser chance of burns. Another classification of burrs are single-use burrs versus multi-use burrs. As the name suggests, single-use burrs are intended to be used on one patient and then discarded, while multi-use burrs are designed to be reused for a number of procedures and patients. For this reason, single-use burrs are manufactured to be disposable. They are not easy to clean or heat tolerant, while multi-use burrs are made for longevity and are autoclavable. Single-use burrs have the advantage that they have improved infection control because they minimize the patient-to-patient transfer of oral microorganisms. They result in lesser clogging of burrs, improving cutting efficiency, and giving less operator and patient fatigue. This also reduces the chair time and keeps the handpiece bearings in good condition. On the other hand, multi-use burrs have the advantage that they can be used on an average of 7 patients, thus producing less waste and being more economical for the dentist. Now let's move on to the design of dental burrs. Dental burrs have blades which are usually in even numbers. For example, cavity preparation burrs usually have 6, 8 or 10 blades. Burr blades are uniformly spaced projections on the burr head which terminate in the cutting edge. Burr blades consist of two faces. The first is the blade face or rake face, which is the surface on the leading edge, and the second is the blade back or clearance face, which is the surface on the trailing edge. In between two burr blades are present the flute or chip spaces, which are depressed areas between two blades. The depressed areas in between two burr blades are known as the flute or chip spaces. The radial line is the line connecting the center of the burr and the blade, and the rake angle is the angle between the rake face and the radial line. This angle can be positive, negative, or 0. In burrs with a positive rake angle, the rake face trails the radial line. The advantage of this is that it increases the burr's cutting efficiency, but the disadvantage is that the cut debris tend to clog in the flute space, and the bulk of the burr blade is reduced with a positive rake angle, which makes the burr more prone to wear and fracture. In burrs with a negative rake angle, the rake face is ahead of the radial line. This reduces the fracture of the cutting edge and increases the longevity of the burr. An example of this is carbide burrs. Negative rake angles produces smaller chips and moves them away from the blade. And if one is cutting a hard substance, a burr with a negative rake angle is recommended because there is an increased chance of fracturing. And since the bulk of the blade is not reduced too much, it reduces its tendency to fracture. Lastly, in burrs with a 0 rake angle, the rake face and radial line coincide with each other. The blade angle is the angle between the rake face and the clearance face of the land. An increase in the blade angle reinforces the cutting edge and reduces the chance of blade edge fracture. Burrs made with a blade angle of approximately 90 degrees reduce the chances of fracture of the cutting edge. Now let's look at the next 3 parameters that determine the design of a dental burr. The land is the plane surface immediately following the cutting edge. The clearance faces may be curved in cases of radial clearance or may be provided with a land which is a plane surface to allow better clearance space. The clearance angle is the angle between the clearance face and the tooth. It eliminates friction between the cutting edge and the work and prevents the burr from digging into the tooth. It also results in an increase in the clearance angle, which reduces the rake angle, thereby decreasing the bulk of the blade. Next, we look at 4 other parameters that also influence the performance and design of a dental burr. First is the head length. Burrs with a longer head reach the full depth of preparation. Post that, we have taper angle, which generates the necessary occlusal divergence while preparation. Then we have the neck diameter. A smaller neck diameter results in weakening of the instrument against lateral forces, but provides greater visibility to the operator, while a larger neck diameter hampers visibility during preparation. But gives additional strength to the instrument against lateral forces. After that, we have the influence of speed. At a given load, the rate of cutting increases with an increase in speed. But this increase is not directly proportional to the rate of cutting. There is a minimum rotational speed for a given load below which the tool will not cut. The flutes of a burr are depressed areas between two blades. Now, a burr can have different numbers of blades. For example, 8 to 10 blades is generally the range used for cutting burrs, while 12 to 14 blades are generally in burrs used for finishing of restorations. A decrease in the number of blades causes an increase in the force on each blade and the size of the chips that are removed. The advantage of a lesser number of blades are that they tend to reduce the clogging tendency of the flute since the space between two flutes is larger, while a disadvantage is that they increase the tendency of tooth wear of a burr, resulting in a reduction in its cutting life and an increased tendency for vibration. An increase in the number of blades, on the other hand, causes less cutting of the tooth material. In the high speed range, no more than one blade cuts effectively at any given time, and the remaining blades are in effect spares at that moment. The next parameter is the spiral angle of the flutes. The cutting action of a burr is uniform throughout a rotation. Each blade starts cutting before the preceding blade has finished. The spiral angle also makes sure that the blade doesn't fall in one single place at any given moment, and it promotes uniformity in cutting and smoothing preparations. At high speeds, blades with a small spiral angle are preferred to improve cutting efficiency. The next parameter that we'll discuss are cross cuts, which are only present in certain burrs. These are notches in the edges of the blade. The mechanism of action is as each cross cut blade cuts, it leaves behind small ridges on the tooth surface. Since notches of two successive blades do not line up with each other, the ridge formed by one blade is removed by the successive blade. This reduces the total length of the burr that is cutting at any given instant and increases the force per unit area due to both cutting pressure resulting from rotation and perpendicular pressure holding the blade edge against the tooth. At low and medium speeds, cross cuts improve cutting effectiveness, while at high speeds, the contact of the burr with the tooth is not continuous, and the high cutting rate of a cross-cut burr is maintained, but the ridges are not removed, leaving behind a rough surface. The next two parameters are concentricity and runout. Concentricity is a static measure, while runout is an active measure. Concentricity is a measure of the symmetry of the burr head when the burr is static. It measures the uniformity and symmetry of the burr at rest and is an indication of whether one blade is longer than the other. Runout, on the other hand, is a measure of the maximum displacement of the burr head from its axis of rotation when the burr is in motion. It occurs if the burr neck is bent or the head is not in line with the axis of the burr. It increases the vibrations of the burr, produces excessive removal of tooth structure, and generates more heat. The average clinically accepted runout is 0.023 millimeters. Heat treatment is used to harden a burr made of soft steel. It preserves the cutting edge and hardens the burr to improve its life. Load is the force exerted by the operator on the tool head and is not the pressure or stress induced in the head while cutting. It is dependent on the speed of the handpiece. A slow speed handpiece would have 1000 to 1500 grams of load, while a high speed handpiece would have 60 to 120 grams of load. There are two types of designs of flute ends. The first is a star cut design in which flutes come together at a common point on the axis of the burr, and the next is the revelation design in which flutes come together at two junctions near the diametrical cutting edge. This design is also considered more efficient in direct cutting. Now that we've seen the basics of burr design, there were certain modifications introduced in burr design when high-speed handpieces started to come into the market. These modifications were the reduced use of cross-cut burrs because they produced rough surfaces at high speeds, and so newer burrs have fewer cross-cuts in them. The next modification were extended heads on Fisher burrs. Carbide fissure burrs with extended heads 2 to 3 times those of normal tapered fissure burrs of a similar diameter have high efficiency at a higher speed when light pressure is applied. And the next modification in burr design were roundening of sharp tip angles of the burrs. This resulted in lower stress in restored teeth and longevity for the burrs. Now, burrs operate by different cutting mechanisms, and the way these mechanisms are evaluated are through cutting effectiveness and cutting efficiency. Cutting effectiveness is the rate of removal of tooth structure, while cutting efficiency is the percentage of energy actually producing the cutting. The efficiency is reduced when energy is wasted as noise or heat. If more pressure is applied by the operator, cutting effectiveness increases, but cutting efficiency decreases. But in general, both of these parameters can be increased by increasing the speed. The next mechanism that comes into play when evaluating strain rate is the next cutting mechanism that comes into play. The faster the rate of loading, the greater is the strength, hardness, modulus of elasticity, and brittleness of the material. For the blade to initiate cutting action, it must be sharp and hard with higher modulus of elasticity than the material being cut. Strain rate helps in exceeding the shear strength of the material being cut. The next cutting mechanism that comes into play is bladed cutting. Bladed cutting causes either brittle fracture or ductile fracture. Brittle fracture is the rapid cracking of tooth structure due to tensile force applied on it, forming subsurface cracks which undermine the tooth structure, thus removing that portion of the tooth structure. This occurs most commonly in enamel and is better caused with diamond burrs. In ductile fracture, on the other hand, the material first undergoes plastic deformation and then leads to fracture. It occurs more commonly in dentine and is better produced by carbide burrs. When diamond particles cut through ductile material, such as dentine, the material flows laterally around the cutting point and will be left as a ridge of deformed material on the surface. Thus, carbide burrs are preferred for cutting dentine and diamond burrs are preferred for cutting enamel. Speed is another factor that comes into play here. For low speed cutting, plastic deformation occurs before tooth structure fracture, while high speed cutting produces brittle fracture. Now that we've covered the basics of dental burrs, let's look at a few diamond instruments from the DIATECH line. These consist of rotary grinding instruments indicated for use on teeth and dental restorative materials such as composites, metals, and ceramics, and so on. They have a working part with diamond grains on it in a galvanic nickel bond on a stainless steel shaft. The main instruments are the DIATECH TOPSPIN 2000 and the DIATECH MULTILAYER diamond. They are indicated in the preparation of cavities, crowns, removal of old restorations, fine adjustment of restorations, crown separation, and endodontic access opening. The contraindications are that they shouldn't be used in patients with a known nickel allergy, as the instrument contains small amounts of nickel and hypersensitivity may occur in extreme cases. Coming to DIATECH TOPSPIN 2000. The burrs consist of diamond-plated spiral flutes along the length of the head of the burr. These spiral flutes collect the water from the aerosol mist and use it to cool all areas of the preparation site immediately. The spiral diamond plating causes an integral cooling and self-cleaning effect which optimizes cutting capacity and promotes atraumatic preparation. The evacuation of debris increases cutting capacity and avoids clogging of the diamond particles. These burrs are primarily indicated for crown and box preparations. DIATECH Multilayer Diamond are multiple layered diamond instruments having a uniform coverage of natural diamond on different levels, especially at the tip. New diamond grids with sharp edges therefore take the place of broken off grains or grains separated from the plating during regular use, resulting in extended cutting life and enhanced cutting efficiency. There is a uniform distribution of the diamond coating for longer and smoother cutting performance. and the shanks of the blades are gold plated, which results in high quality and safety. DIATECH Speedster burrs are concentric burrs made from a solid single piece of submicron grain carbide designed using CAD. They result in a consistent blade contact with the tooth surface for smooth cutting. There is reduced vibration and chatter, which prevents damage to tooth structure. They have a high cutting efficiency, which reduces preparation and chair time, and a high wear resistance, resulting in durability and longevity. The burr heads are extra long and have an especially long cutting section, which makes them useful for bulk reduction of crowns and bridges during preparation and intraoral titanium abutments. They can be used to cut all types of materials, including amalgam, gold, porcelain, enamel, and PFM. DIATECH Speedster can be used in cavity preparation, removal of old restorations, crown cutting, and crown preparation. A study comparing the cutting efficiency and working life of different kinds of tungsten carbide burrs showed that DIATECH Speedster burrs had the highest cutting rate, the largest cutting efficiency, and the largest lifespan per minute. And these values were statistically significant in comparison with all the other burrs that were tested. That brings us to the end of this WhatsAppinar. I hope you enjoyed and had some useful takeaways from the information that was presented. Thank you.